want to recap where we were at with the boat problems. We've been doing a lot of stuff lately, and I just want to make sure everybody's on track to restart again when we meet again. So we had the situation where two boats start at the same place, go off in different directions, and you want to know, and at different speeds. And after a certain amount of time, you want to know how far apart they are. And the way we posed it was we want to know when do they get to a point where that's 100 kilometers. Well, I want to point out some simplifications that you guys made and then talk about sort of the geometrical core of the problem. Okay, so there's two things that kind of complicate this. One is the mixture of the distance, rate, and time information. And of course, that's all about d equals rt, which you can never do too much of, especially if you're in pre-calculus, because calculus talks about that all the time in a very sophisticated way. And then the second one is the influence of, let's call this angle theta. If that's a general angle theta, that makes things complicated. This we'll put back into the problem later, but I want to actually focus on this one first. So I actually am going to simplify both of these guys and then think about, well, what would happen if you put back this complexity here? Okay, so here's the simplest. Here's what we found. I'm going to recap what you guys found. If they go in exactly opposite directions, so in other words, if theta is 180 degrees, then we've got a time, they go for a time t, and that's the variable that we were trying to figure out. Okay. And this guy goes, let's see, let's say the speeds are v1 and v2. The v is really for velocity, but we're just going to use it as in terms of a speed. And so this guy is going to go d equals rt is v1t, and this guy's going to go v2t. So that's the distance, rate, time stuff coming in. The fact that these guys are VTs. But then the real crucial geometry is that the distance between them is the sum of those guys. And that happens to have a common factor of t. And that needs to be 100 in our problem. Okay. And what I really want to focus on is simply this idea that if two segments are in opposite directions, you just sum the lengths of the segments to get the total distance, the distance between these 2 points. Okay. So that was one of the cases, 180. Let me erase everything here. Another case, which people tend not to do because it seems so trivial maybe, is if they're going in exactly the same direction. So this guy, let's say V1 happens to be slower. And so this one is V1t, and this distance is V2t. Then we're talking about the distance between 2 points on a number line. And so the distance is going to be V2t minus V1t. Still a common factor. Now, it happened to be that V2 was bigger than V1. If it was the opposite way, this would give you a negative number. We don't want a negative number, but we can fix that by just putting absolute values everywhere. Okay. And so, again, the way we would solve the explicit problem is set that equal to 100 and solve for t. But the geometrical core of the problem is this idea that the distance, if they're in the same direction, is the absolute value of, let's call this like x1 and x2, just the distances. Absolute value of the difference. And now, because it's absolute values, it doesn't matter which one I put first, x1 minus x2 or x2 minus x1. Okay. So that's two special cases where we added or subtracted and remembered to take absolute value of two distances. Those are one-dimensional problems. That's not what we usually think of as geometry. To get into 2 dimensions, we look at the third special case that we looked at. So let me go ahead and use that notation x1 and x2 again. So here, when they're 90 degrees. So what was the angle before? Sorry, when they're in the same direction, just one more thing. Here the theta is 0 degrees. So we got 0, 180, and now 90, or 0, pi, and pi over 2 if you want to use radians. Now, usually with these geometry problems, we actually do use degrees, so make sure you get familiar with going back and forth on the calculator, for instance. So here, we wanted to know when this would be 100. Okay? Or in other words, in general, the real geometric problem is how does this distance relate to these guys? Well, that's super famous. That's Pythagoras. And the distance squared is x1 squared plus x2 squared. Okay. Now, I want to compare that. So this is the 90-degree version. And I just want to give you a hint as to how this is going to go in a more general direction. Remember the 180-degree direction. Let's actually look at the distance squared. Remember, the distance there was just x1 plus x2. And if you square that, you just get the square of the sum. Now, that is different from the sum of the squares. It's totally different. You've got these guys, but you've got 2x1, x2. And in the 0-degree case, distance squared, let's see if you can see that a little better, it was the absolute value of the difference, and square it. You know, if you square an absolute value, squaring already makes things positive, so the absolute value isn't necessary, and so you just get the same thing as if it was parentheses, and it's very similar, but now this is minus. Huh. Suddenly these things start to look pretty parallel if you do it in terms of distance squared. You either don't get a term in the middle for 90, you do get a plus 2 in the middle, or you get a minus 2 in the middle. And what we're going to be doing is we're going to be generalizing that. What about the other possibilities for theta? And it's just going to turn out to look very much like these examples. So that's what we're going to be still investigating in class. The problem is, what if you had just a general angle, theta? And I've got x1, x2, and I want to get the distance between the boats. Or if we want to use the standard letters, we often use like A here, B here, and C here. So the idea is, suppose I know this. This isn't exactly how our boat problems work, but this is a simpler version of it. Suppose I know these 3 pieces of data. Suppose I know how far this boat went, how far this boat went, and the theta. Can I figure out how far they are apart from each other? If I can't do that version, I certainly can't do the version where I have this be known and I have the unknown time and put all the d equals rt in it and stuff like that. Okay, so that's the idea, is known are a, b, and theta, and we want to get c. And let's see if we have any right to believe that we could do that. Well, if you think about, like, take 2 fixed rods, put a hinge here, open them up to a specific angle, and have this be a rubber band. Is the rubber band some particular fixed length? Yeah, it's a completely known length. There's only one kind of triangle that works here. And we have a theorem from geometry that says that. That's SAS. SAS says that side angle side, 2 sides and the angle between them, and that's very important, is enough to determine the whole triangle, in particular the length of this side, and the other angles as well. But let's focus on getting this side first. Okay, so that's the problem we're going to have. And one more thing, people were interested, when people were looking at this before in class, I saw a lot of people relating it to like north, south, east, west, which makes sense because we've been doing a lot of that with polar and complex numbers and stuff like that. I'll give you a hint, that's not super useful. There's nothing special about north, south, east, west here. There's good reasons to do things like drop altitudes here, but we don't really want to artificially relate it to north, south, east, west. That doesn't actually help. Okay, and now you guys are going to be ready to jump back into that.